Hi, I'm Nathan Hara from the University of Geneva. Welcome to the third tutorial on the online platform DAIS. In the first tutorial, we have seen some basic features of DAIS through the case of 51peg. In the second case, we have seen a more tricky example, which is 55 Cancri, and we have seen some capabilities of DAIS with model selection. And in the third tutorial, I'm going to show you what you can do to correct the stellar activity and to select very precisely the points that you want to analyze. Okay, let's get started. Okay, the example I'm going to show you here is HD 21693. What I can see is harps data points, only harps, which means that we don't have to deal with different instruments and the problems that go with it. I have here the parallelogram of this data, and I can see that there is a signal at 4,000 days. And in this range of period, you might expect that this comes from a magnetic cycle of the star. And to check this, I'm going to look at the S-index, which is an activity indicator. And if there is a magnetic cycle, this should be seen in the S-index. And indeed, we see a very clear sinusoidal behavior and a lot of power in the range of periods of 3,000 for 4,000 days. Okay. And to show this even more clearly, I can go to the correlation segment. Here I have on the x-axis the radial velocity, on the y-axis I have the S-index, and the v-axis is in fact a color code, meaning that in purple points are at the beginning of our time series, and dark red points are at the end of the time series. We see a Pearson correlation coefficient of 63, which is significant, and even by eye, you can see a very clear correlation between the S-index and the RDS. Like in the case of 55 Cancri, I could fit a sinusoidal function or Keplerian function at low frequency here. But here, since I have harps data, I have a good quality S-index, and I can use this S-index to detrend the data. To do this, I'm going to the detrending and activity in parentheses box, and I'm going to add push the plus button. What it does is to add a linear predictor to my model. And here, this linear predictor is the S-index time series. And you see that if you do this, you clean this part of the parallelogram so that a very clear signal pops here. But you could argue that in the S-index, I have not only low frequency variations, but also high frequency variations. So if I fit this S-index directly, maybe I will introduce some variability in the data, in the radial velocity data, which is spurious. So I'm going to do something more. I'm going to smooth the S-index. I'm selecting here a kernel smoother, which is Gaussian, and a time scale of the smoothing, which is half a year. This is the default value, and this is what I'm going to use here. And if I fit this smooth S-index, I see that pretty much nothing changes, but the risk of introducing high frequency variation in the data is less. I have now a very clear signal in the parallelogram at 53 days, which I'm going to fit. And I see another clear signal at 22 days with a false alarm probability below 10 to the minus 10. I'll look at the log10 FAP field as before. I'm going to fit it also. I fit everything together. And I don't hear the maximum peak of the parallelogram, which is, I believe, no, maybe this one. has a false alarm probability of not even below 10%. So there seems to be nothing else in the scene. But maybe my noise is poorly estimated. Maybe the noise level that I have with my nominal uncertainties is too small and it is hiding some signals. So I'm going to fit the noise level. But it seems like nothing changes. So now I can compare my result to what has been published. This data comes from, has been made public after this paper has become public. Udry et al. 2019, and in this paper they have unveiled 2 planets at 22 days and 53 days, which is what we have. So that's pretty reassuring. Something I might want to look at still is the phase folding of the data. So I'm going to click on this icon. So this is just as the name suggests, phase folding is folding the time series on the period of one of the planets, here 53 days. If I want to phase fold the time series on the other period, I just click again on phase folding. And if I want to go back to the time series, I just click on time series. So what is striking in both cases is that you have 2 points which are standing out. Here there seems to be 3 points, but in fact this point is the same as this one. It's just because of the phase folding. So I'm gonna remove it to see what happens if I remove it. And to do this, I click on the point and I go to data selection, remove points. I'm gonna remove this one as well. And what I see is a new peak in the parallelogram at 10 to the minus 2 false alarm probability. 1% FAP is usually not enough to claim a planet, but it is enough to claim a candidate, to say that you have power there and that this might be a planet. And in the paper here, this paper, they don't mention this candidate, so maybe we have found something new. But something to mention is that HD 21693 is a G-type star, and the rotation period is estimated at 35 days. And you would not typically have a very clear peak at 35 days in the radial velocities or ancillary indicators, but power around 35 days and around 35 days divided by 2, the first harmonic of the rotation period. And here the peak we have is at 15.7 days. That's close to the a harmonic of the rotation period. This can be seen also in the S index. Here I'm reselecting the S index. And I'm going to detrend the S index, not with itself, because that would not make any sense, but with the low frequency version of the S index. So I'm basically removing the low frequency variation in the S index. And what do I have in the residuals? I have a peak at 35 days, and I have a peak at approximately half the rotation period at 15.8 days. So that this suggests that the variation that we see in the radial velocity is real, but it is due to the rotation, to the stellar features on the surface of the star, which appear in the radial velocity at the rotation period of the star or its harmonics. If I wanted to redo the analysis with the points that I've deleted, because I have no obvious reason to have deleted these points, maybe they are correct and I want to include them in my analysis anyway. So I go to data selection and I will click on reload deleted data points. And now when I look at the phase folding, I see them again. and the peak in the periodogram has disappeared. Now, let me show you one last thing that you can do is still in the detrending activity box. I'm going to add another field with the S index. But instead of clicking on fit the semi-amplitude, so fit a linear predictor, which is the S index, I'm clicking on scale jitter. So here, what it does is to add an error term. So it goes in the noise model, and this error term is proportional to the S index, or the S index, which is smoothed with a Gaussian distribution, or a Gaussian kernel, or a box kernel. And here it doesn't change much. And you see that it increases a little bit the error bars, so that this outlier, at least this one, is still something that does not seem too improbable. This point is still very far from the rest of the phase folding. So there is probably a reason. Maybe there was a cloud, maybe it was due to the observing conditions. And now in the periodogram, I see still a peak at 15 days, some power around 30 days, and another peak at 9 days, which might be the third harmonic of the rotation period. Okay, so this concludes this third tutorial, which was aimed at showing what you can do with the stellar activity in DACE. The next one will be on the DACE notebooks, which allow you to explore even more advanced capabilities. And that's it. Thank you for your attention, and have fun with DACE.